Assalamualaikum warahmatullah. Good afternoon. Can you hear me?
Walaikum assalam wa rahmatullah. Yes, we can hear you, Prof.
Thank you. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Very good afternoon to all. So today is 13th of January. Okay, so we are going to see chapter 5C, another case study, which is on industrial hydraulic actuator with the real data, okay, from the experiment, okay, taken by the research student. So the model that we are going to use is the ARX modeling, okay, as we learned before in chapter 3. So there is this outline for these presentations, which will be some theoretical on system ID, model identification using MATLAB, feedback control system design, and simulation using Simulink. So as we know that in the system ID, deriving a mathematical model is based on the measurement between the input and output data of a certain system dynamics. So in this case, we are going to capture data from industrial hydraulic actuator system, okay, input-output data for the dynamic system. So why I call it dynamic? Because the pistons is moving from forward, backward, compared to the hot air blower system, which is known as a static system. Static system meaning the process is stay over there, it's not moving. Okay, it's not moving, only the air moving from the beginning, of the point to the end of the point, but the system is static there. Okay, so the system is not moving, but in this case, the system is dynamic. So the piston is moving from backwards to forward to backwards. That's why it requires design and implementing high performance control system. Then the obtained model will need to be validated to verify its preciseness before it can be used. This is we will apply validations which comparing the output of the obtained model and the output of the plant. So using part of the experimental data, we reserve for validation purpose. For example, you are captured 1,200 data. So the theory said that you divide into two. The first 600 for estimations, okay, and then the remaining 600 is for the validation. So this procedure is stated and depicted in this flowchart. Okay, the experiment, the model structures, selection, the model estimation, the model validations, which is start from the experimental, which is we design the input for the system, the PRBS or the sign input, or maybe the step or impulse. Then we choose the model structure, linear, ARX, 331 with 3 poles and 2 zeros and 1 delay, for example. And then we estimate the model using a least square or generalized least square. And then we validate the models using a best fit or AIC or FPE, final prediction error. Then if the model validation show a good percentage, or a very small FPE, final prediction error, or very small AIC, then the model is accepted. Then we straightforward accept it and put in the Simulink for next step, which is the controller design. If not, we have to estimate the model again, or maybe we have to choose another model structure, or maybe we have to do the experiment again. This is the process that we have to carry out during the experimental. To set up the experiment takes time, but to capture the data, maybe about 2 minutes or 5 minutes, okay, depends on the how long the data and the sampling time that you design. And then the important thing is to estimate the parameter, okay, of the transfer functions, the coefficients of it. We call it as parameter adaptation algorithms, so that it gives you a very small error, or we call it as a mean squared error, okay, over here, where you have what we call that the estimation YK and the real value, which is compared, and then this error will be fit to the parameter algorithms, okay, and this will be adjust, the algorithm will adjust the parameter of the discrete time model, and then give you the value of the estimated parameter model. So parametric model structure are usually represented by difference equations, okay, which is shown here, yk plus a1 yk minus 1, a yk minus na, and so on, equal to b, where y is the output, u is the input, ek is the noise, or the, what do you call that, as a stochastic part, okay, and then d is the time delay, and na is the number of poles, and nb is the number of zeros in that particular models that we get. So we have a few model structure mentioned by the guru of the system ID, which is known as Professor Aljun in his book, okay, in 2002. He proposed start with the simple linear model first, which is the ARX models. And then if the noise is significant or dominant during the experimental, so he proposed another model, which is RMX model, which will include the deterministic part and the stochastic part of the system. Or you can use an output error model, or a box and Jenkins model, or other model that you feel suitable. In the system ID toolbox, there are so many models, okay, which is known as, I will show you in that particular toolbox, right? So for this purpose of the class, so we use the basic model, which is ARX model, which is forming a few other model structures. So RMX model, as we learned in chapter 3, is represented by this polynomial, that is a general linear polynomial model that I teach you, where we have to assume the D, the E as 1, and then we get this equation of A equal A multiplied by Y equal to B multiplied by U, the input, plus C, which is multiplied by the noise, okay? So A, B, and C is the polynomial, okay? Is a discrete polynomial, where you have the Z operator, okay, in the bracket. And C is equal to 1 plus C1, Z minus 1, and so on. Or maybe this is the RMX model. And the OE models shown here, where you assume A is equal to 1, C is equal to 1, and just the remaining B, D also 1, and F, which is considered part of the polynomial of the system. Same as well to the Box and Jenkins models, okay, where we assume A equal to 1, B, C have a value, okay, D and F have a value, which is shown here, but not suitable for the control system design. But anyway, the important thing is the general parametric model, which is shown here, where you have the A polynomial, B over F polynomial, C over D polynomial, okay? So A usually related to the output, B and F related to the input, C and D polynomial usually related to the stochastic part or the disturbance part, uncertain part, which is known as noise. So in hydraulic system is a robust system. So we have to be careful in designing the input signals that we will inject to the industrial hydraulic system. So as you know that hydraulic system applied in robotics, in the crane, or in any aeroplane, aerospace, and so on. Okay, we use hydraulic actuator for what do you call that? Heavy duty job. Okay, so it needs a lot of pressures. Okay, that's why we have to generate a special input signal. Okay, which will give you the good parameters ID that required signals that are many frequencies inside, or we call it as rich in frequencies. We acknowledge that we have learned and studied and designed the pseudo-random binary sequence, which is PRBS. But PRBS is not suitable for the industrial hydraulic actuator system because to generate PRBS, to generate a sequence of the different width square pulses, the implementation is a little bit difficult, okay, compared to the hot air blower system, okay. If a temperature system is okay to use PRBS, but for hydraulic system, since it was a dynamic system, so we need to use a suitable signal for it, so we choose sinusoidal signals, which is more suitable, which is more relevant and easy to generate compared to the PRBS. Okay, so we can generate PRBS simply using this formula. Okay, U is equal to summation AI cos omega I TSK, where A is the amplitude of the sine wave, W is the frequency, and TS is the sampling frequency for the input sinusoidal signals. Okay, so we can write this formula in MATLAB, and then we interface with the system using a real-time MATLAB workshop and using a national instrument card, which is compatible, okay, with the real-time MATLAB workshop. So we have there is a parameter, we call it as a P, where P is the n divided by 2. N is the number of model parameter that needs to be identified. Okay, maybe in parameter estimations in chapter 4, we have n equal to 2, which is the A and B. Okay, but if P is equal to 3, so we have to have maximum of 6 model parameters, okay, that can be obtained in the signals that we generate. So that's why we have to use the 3 frequency, which is the omega 1, omega 2, and omega 3, with the amplitude of A1, A2, and A3, with the same sampling time, which is TS, TS, and TS. The K is the sequence number, Okay, it starts from 0, 1, 2, 3, and so on. Okay, in the input signal U. So we derive from the measured input and the output signals of a real plant that needs to be identified. Okay, the ARX parametric model structure we choose due to the fact that it is a simple structure and represented by the simple linear difference equation by assuming noise is 0 or very small, which is we assume that the signal noise ratio is high or big. It shows that the denominator part of the noise is very small and can be ignored. So that's why the ARX model become Y over U equal to B divided by A Z operator. Okay, and this ARX model for hydraulic system, we have to be careful that the sampling time that we choose, okay, must be according to the spec that we want. If the spec want the minimum phase model, so you have to use a large or high sampling time, sampling time. Okay, but if the spec design want a non-minimum phase model, which is we have to use a small value of sampling time. So what is the concept of this model? So let me show you in the Z plane. Okay. I mirror first the signals. So can you see? Show me, can you see? Hello, can you see? Are you sleeping? Hello?
Yes.
Okay.
Yes. The plane.
Okay, okay.
Yes, Prof.
So is a non-minimum phase model. Okay. So let's say we have a third order. Okay. 3 poles and 2 zeros. Okay. Right. So this one we call it as a Z plane. Is a discrete, similar like S plane in continuous form, but in discrete form, we call it as a Z plane. And in the Z plane, we have a what do you call that? A unit circle. Okay. Okay. So when you have a poles, which is located like this, okay, okay, and zeros, which is located here and here, okay. So this one we call it as a non-minimum phase, okay, non-minimum phase model, okay, because there is 1 0 outside the unit circle. Okay, so this is a unit circle. Okay, but the system is stable. System stable due to all poles inside unit circle. Okay, but what happens if the system is a minimum phase model? Okay, so we are using the same thing, which is 3 poles and 2 zeros. Okay, so we have a unit circle. Okay, and then the poles is side and the zeros is here. Okay, so this one is, we call it as a minimum phase due to all zeros inside unit circle. Okay, and the system is stable due to all poles inside unit circle. Okay, so when the system is unstable, okay, so the system is unstable. The system is unstable when okay, when we are using still same third order system. Okay, okay, so this is when the system is unstable. Okay, and minimum phase. Minimum phase because all zeros inside unit circle, but unstable due to one pole outside unit circle. Okay, so now I have a questions. Okay, I have a questions. If we have this system, same system, third order, I do it first. Okay. So what is your observations? What is the system stability? And is it minimum phase or non-minimum phase? So the system is third order because the 3 poles, 2 zeros. Okay. System unstable due to one pole outside unit circle, and system is non-minimum phase due to
1 0 outside
1 0 outside
unit circle.
unit circle. Okay, everybody okay? Inshallah okay? Okay, eh? So there is a recording YouTube on that. So don't worry if you miss the class or you come late. Okay, should be no problem. So continue to the slide here. Okay. So this is a non-minimum phase and minimum phase from functions. A non-minimum phase on function has zeros in the right-hand side of S-plane. So this is S-plane. Okay. So S-plane and Z-plane is different. S-plane in continuous time. Z-plane is the discrete discrete time. Okay, what is the difference between it? Discrete is the data from the continuous time. We use a sample and hold. Okay, we use a sampling. So like a switch, sample and hold. Okay, tick, tick, tick. If you sample 1 second, so the switch will acting every 1 second to capture the data. 1 second, 1 second, 1 second, 1 second. If you sample at 50 milliseconds, so it will be faster. Okay, I think this is more faster compared to the previous one. And a minimum phase transfer function has all its zero lie on the left hand S plane. So this one is in S plane, the one that I described in a Z plane, but the concept still the same. Okay, so this is a sample of it. You can see that this one is the non-minimum phase, 1 zeros on the left hand side of the S plane. Okay, here. And this one is all zero located on the left hand side of the S plane. Okay, so you have to delete this one first. Okay. And in terms of the frequency response, in the phase form, both plot phase form, you can see that the minimum phase start from 0, peaking at the 90 degrees between zeros and pole, and settling at 0 degrees again, compared to the non-minimum phase, which is started at 180 degrees positive and slope down to the 0 degree. Okay, for the both plot presentations. So parameters approximation can be obtained using a recursive least square algorithm. Okay, so least square, we have a simple least square, generalized least square, and recursive least square. This equation of recursive least square is using a regression vector, which is given by psi k transpose this vector, which is equal to the psi 1, psi 2, and so on. And approximate parameters vector is given by the theta approximate transpose A parameter A, A1, A2, A3, and B1, B2, B3. And it will produce you the predicted error, which is the error is the difference between the actual value of output y, okay, minus the estimated value of y. Okay, that's why it's written as y minus y. Okay, there is cap between that. Okay, and then it's multiplied with the psi, then update the approximation, and then the correcting vector. So it will give you the k value, okay, the correcting vector. And then the effect of errors due to truncation and runoff during computation of covariance matrix PK is shown here with the UD factorization method for computing. This recursive least square need to do a programming, okay, because the solution is quite long, okay. So we need to do a programming in order to do the recursive least square. There are so many algorithms of recursive least square. You go to the Google and write the recursive least square estimation program or algorithms. So there is a lot of samples in there which give you this method is very fast convergence and then very effectiveness and the symmetry of PK, okay, the covariant matrix is guaranteed. So modifications to the correcting vector with the reference of a UD factorization method is using the algorithm shown here, which K, FK, GK, alpha K, and the UK. So you don't have to worry about this, okay? This one is just a recursive least square concept and idea. Part of it is we need to validate the data using the remaining half of the data that we captured. and acceptance or rejections of obtained model based on the criteria, FPE, okay, final prediction error. We call it as the Akaike's final prediction error, or Akaike's information criteria, also CAM. Best fit is the popular one, and others. Okay, so best fit, AIC, and FPE, or we call it as FPE, is the best or popular validation method that apply in the model input-output presentations. This criteria show the preciseness of the approximate model as compared to the true model. So the formula for FPE is given by FPE is equal to V, 1 plus D divided by N, divided by 1 minus D divided by N, okay, where V is the loss function, D is a number of approximate parameters, and N is the number of samples. Okay, so V is equal to E square divided by N, E transpose multiplied by E divided by N, and EK is the error vector, okay, represented by this error vector. Power of T, T is the transpose interchange between rows and column. The selection of model from various order is based on the smallest value of the FPE. Okay, as long as small, 0.00 something, so we call it as the small error and as acceptable. The next model is the AIC for model validations. So AIC is using a logarithm base, logarithm 10, base 10, logarithm of V multiplied by 1 plus 2D divided by N. Okay, so selection of model, various model order is based on the smallest value of AIC. And the best popular one is the best fitting criteria, or best fit in percentage form, where 100 multiplied by 1 minus normalized y cap minus y, and normalized y minus y bar, the average. Okay, so y is the true value, y cap is the approximate value, and y bar is the mean value. Okay, so model selection will be based on the highest percentage value. So this is the plan that I will describe to you. Okay, the dynamic industrial hydraulic actuator system. Okay, so you can see that there is a 4-wire, 4 piping. Okay, the input piping and the output piping, which consists of the oil that moving in this pipe, and there is a controller here, is a proportional valve, okay, that delegates the liquid, okay, to the input pressure and the output pressure. Okay, so there is a pressure sensor, is on the left and on the right. Okay, and is a bidirectional cylinder which is moving backward and forward, and on top of it is the positional transducer that attached to the cylinder here. Okay, the piston. So when the piston is moving forward and backward, so this positional transducer also will follow and measure the distance or the displacement that move by the pistons of the cylinder. Okay. So the important thing is this controller. Okay, because this controller will give you the opening of the valve. Okay, so the opening of the valve can be illustrations by this circle. Okay, so this one considered as a block, okay, that will block the liquid from flow through the pipe. So the liquid will flow here. So this one is what we call as a half flow. Okay, so this one is the opening. Okay, the opening 100% or opening 0% of the proportional valve is based on the controller, okay, that you design, okay, controller that you design. So once the flow is 100% open, the opening of the valve is 100%, so you can see that it moves very fast, okay. The cylinder will move very fast because of the high pressure of the liquid that flow inside the pipe. But if the valve of the pipe here, the black pipe, is open, only 25% or maybe 10%, and the rest is blocked. So you can see that the flow inside the pipe will be slower due to the low pressure. Okay, so you can see that it slow down. Okay, the cylinder, the pistons of the cylinder is slow down. Okay. So this hydraulic actuator is data taken from it is the bidirectional cylinder, okay, from a Novotechnic company. So the pistons is 25 millimeter, the piston rod is 16 millimeter, the stroke is 400 millimeter. Maximum stroke meaning that the maximum it can goes forward and backward, 400 mm, which is equal to 40 centimeter. Okay. And the piston area ratio is 1.6 ratio 1. So the position transducer is using the inductive tap, which will follow the movement of the piston. So the pressure fluid flow is controlled by the electronic control valve, which is the proportional controller, and the control valve is proportional and bidirectional type. Okay. The input valve is plus minus 10 volt, and the current range is between 4 to 20 milliamp. Okay, so in order to create pressure, of course, we need a pressurized pump, okay, that can regulate the fluid source up to 2,300 psi or 160 bar. Okay, so really very high pressure. So this is the motor pump that will create the pressure. Okay, and then this is the valve, okay, the control valve. And then the oil reservoir where we accumulate all the liquid here and will be sucked by the motor so that it will regulate the pressure throughout the pipe. And the valve here, servo valve, okay. And then this is the cylindrical and the LVDT attached. So the pistons is here and the LVDT will be attached here. Okay, LVDT stands for linear variable differential transformer. So it's a sensor that detects physical signals, which is distance or displacement in millimeter, and convert it to the equivalent voltage value. Or maybe we don't want to use LVDT, we also can use this sensor for displacement of measurement. We call it as a drag wire sensor. Okay, as drag wire sensor. Okay. So this one is attached to the pistons, so it's a wire. So when the wire moves back forward and backward, it will measure the distance and convert to the equivalent voltage value. Okay, so overall the system is shown here. We put some load on the pistons, okay, and then we capture the data using a national instrument. And then we save it in the computer for display and data processing. So I showed you the movie last time during the first class, okay. So to save the time, so I don't show the movies. We straight away go to the case study. Okay. We have a break about 10 minutes, okay. 10 minutes break, then we continue at 3 o'clock, okay. Can or not?
Can, sir.
Can, huh? Okay, we stop for a 10 minutes break. Assalamualaikum and good afternoon. We continue again the second part of today's lecture. Okay, by looking at the case study, okay, of the model identifications. So we designed the input signal to the plant, okay, generated using three different frequencies, which is written here. Cos 0.5 TSK plus cos 2 TSK plus cos 5 TSK, where TS is the sampling time, K is the sequence, right? So you're using three different frequency for the input signals. The reason why, because models order obtained limited to second and third order. And the higher order models may produce inaccurate models or unstable output. And the third order model will represent the nearest model of the true plant. So this is the input signal generated. And how to generate it, I attached in the program in the WhatsApp that I forwarded yesterday, kinput.m. And this signal will be injected to the hydraulic system. So we have three types of data, model A.m, model B.m, and model C.m. So these data have three different sampling time, which is 45 millisecond, 50 millisecond, and 55 millisecond. Okay. So we want to see the variance of the sampling time, because low sampling time will give you non-minimum phase, and high sampling time will give you minimum phase model. Okay, so I already WhatsApp yesterday in the WhatsApp. I hope you already download it and save it in your laptop. Okay, so model A is derived from model A.m, model B.m, and model C.m. Okay, so all model will be treated. So we start with the sampling time of model A, which is 45 millisecond. So 45 millisecond is 0.045 second. Okay, because in the system ID toolbox, we have to key in the sampling time. The unit is second, not millisecond. So the input output data will be here. Okay, you can see that okay, far away. We have this is the input and this is the output. Okay, looks similar. Okay, but in terms of amplitude is different. So we have two parts. Since it's 1,000 samples, so we take the first 500 and the remaining 500 for estimation. and 4 validations. And then we use the system ID toolbox. We use the pre-processing data, then estimate, then we choose the model structure as ARX331. So 331 meaning that we suggest that the poles is three poles and two zeros, and one delay. Okay, so this is we get the value from the MATLAB. Okay, at the model output. Okay, where the graph will give you the measured value and the estimated value with the best fit, and it give you the numerator of B and the numerator of A, which is correspond to the model ARX331. Then we simplify because this one can be factorized. Okay, so we factorize it. Okay, then we equal it to 0 so that we can get the value of the zeros from the numerator B. Okay, 2, 0. And here also you can what do you call that? Get the value of the poles from the A polynomials. So 3 poles. Okay. So you also can get this from your calculator. Okay, by entering the 1.094 and negative 0.443. Okay, in your calculator, and then find the roots. So it will give you the 2 zeros value. And same goes to the A polynomial where you key in number 1, minus 0.9139, minus 0.2599, and plus 0.1743 into your calculator. Then you will get the value of 3 poles. Okay, so the value of zeros is shown here. After you factorize this, okay, you will get Z minus 1.4 and 0.3146, meaning that the first 0 minus 1.4, okay, is located here, which is the outside of the unit circle. So meaning that the system is a non-minimum phase. And then the poles value, which is 1 minus 0.46 plus 0.377, all poles are located inside the unit circle, including this 0. Okay, so all poles in the unit circles, meaning that the system is stable, no issues. System is stable, but is a non-minimum phase due to the fact that 1 zeros, which is minus 1.4, is outside the unit circle. Then we find the model output. Okay, after we divide into 2. Okay, so the result is shown here. Okay, the plan and the model. Okay, plan meaning the measured value, the real value, the actual value. Model is the estimated value or predicted value or approximated value. Okay, or simulation value also can. That is the terms used by the books. Okay, so the percentage is 94.6%. Okay, with the loss function 0.002, which is very small, FPE 0.023, which is very small, and AIC is minus 6.094, which is negative below 0. Okay, and this model is accepted based on the values criteria, FPE and AIC, a good percentage best fit. Then we do another experiment. This time around, we change the sampling time at the data logging system. We change from 45 millisecond to 50 millisecond, or 0.050 second. We do the same thing, capture the data, plot the data, divide into two, the first half for the estimations and the second part for the validations. Then we get another polynomial for ARX331 model structure, which is different in terms of the value of the coefficients. Okay, so as usual, we factorize, okay, the numerator part, which is here, and this one is equal to 0. Okay, so when equal to 0, this one you have a 2, 0 value, and this one you have a polynomial A, you have a 3 poles, okay, with time delay 1. Okay. Then the zeros value will be minus 1.1277, and the another zeros is 0.3714. So you can see that there is 1 0 outside unit circle, and this 0 is inside unit circle, which is this one. Okay, and this one is this one. Okay, and for the poles value, we have a 0.0963, which is very far here, nearly 1, minus 0.4391, which is here, and positive 0.4338, which is here. Okay, so all poles inside the unit circle, there is 1 zeros outside the unit circle. The system is stable and non-minimum phase. So the model output, the measured and simulated value is shown here, okay, with the best fit 94.54%, above 100%, with the loss function 0, FPE 0, and AIC 0. Okay, so smallest value of criteria, FPE, AIC is accepted due to the small value and good percentage best fit. Then we conduct another experiment, which is model C, which is we use the higher sampling frequency. We increase to 5 milliseconds from 50 milliseconds to 55 milliseconds. When you plot the data, okay, so we have 1,500 samples data. The first 750 for estimation, the remaining 750 for the validations. Then by using a system ID toolbox, you get a B polynomial and A polynomial, which is this one is equal to 0. This one have 2 zeros, okay, and 3 poles, okay. Then after we plot it, we observe that the 2 zeros minus 0.643 and positive 0.142 is inside the unit circle, both of it. Okay, so both of it, and the poles are here one, the other one is here, and the other one is here. So all poles inside the unit circle, all zeros inside the unit circle. So the system is stable and the system is a minimum phase. Okay, minimum phase model. And the model output is shown here with the best fit of 93%, loss functions 0, FPE 0, and AIC is 0 below, which is negative and is accepted. So the conclusion is minimum phase model can be obtained using a large value of sampling time. Non-minimum phase model can be obtained using a small value of sampling time. So now I will show you how to use the MATLAB, okay, in order to do the one that I teach you just now. So I closed it. Then I open MATLAB. Okay, I start first, then I will ask you to use the, I start with model A, then model B and model C will be run by two of you, okay? I will share and enable the sharing button. So I show first the MATLAB. Okay. Share screen, MATLAB. Okay, can you see the MATLAB?
Yes,
Hello?
Prof.
Okay, can you see, eh? So you make sure that your model A, model B, and model C at your desktop in front of your laptop, okay? So now I will open, because I will open the file that I gave it to you at the desktop, which is model A.m. Okay, so this is the model A.m. Can you see? Can you see?
Yes, Prof.
So you have a data with three vector column, which is column 1 is the sequence 0 to 1200, I think. And the second column is the voltage value of the sine wave, okay? And the third column is the column for the displacement or the distance in millimeter, okay? So if I browse the data from 0, 1, 2, 3, okay, until the end, so we have about 1,200 data, okay, and I name the volt data column number 2, VOLT, which is the input, and DIST is the output, which is the third column, okay. So first column is just a sequence number of data from 0 to 1199, meaning that the length of the data is 1,200, okay, 1,200. So what is the period of the experiment? Okay, the length of the data is 1,200. The sampling time is 45 milliseconds. So what is the period of the experiment? Saravanan. Saravanan? Saravanan sleeping or not attending the class? Hello?
Yes, sir.
What is the period of the experiment? The length of data is 1,200. And the sampling time is 45 milliseconds. What is the period of the experiment? Get it? No? Al-Kali? Muhammad Al-Kali?
Yes, Prof.
What is the period of the experiment? The length of the data is 1,200. The sampling time is 45 milliseconds.
It's 45 divided by 1,200.
Huh?
45 divided by 1,200.
No.
Prof, the
No,
period
from
is,
Muktaba. Muktaba. Hello, Muktaba.
Prof, it's 45.
Huh?
45.
What?
Prof, it's 54 seconds.
Who said that?
Hassin.
Hassim. Yes, the answer is correct. The period of the experiment is 54 seconds. How I get 54 seconds? The length of the data, 1,200 multiply 45 millisecond or multiply 0.045. 1,200 multiply 0.045. So you will get 54 millisecond, almost 1 minute. Correct. Hello, guys.
Yes, sir.
Okay. So now after you see the data, now you press the run. Can you see the run there? The triangular run. Here.
Yes,
Can you
Prof.
see? Hello?
Yes, Prof.
Okay. You press run. Okay. Then they will ask change folder because your folder is now in desktop. Change your folder. Then the model A has been run. Are you sure? So we call the data volt, V-O-L-T. Volt, okay, for the voltage value. So that is the volt and the distance, D-I-S-T. Data, is it available in the system? Yes. Okay. Then you want to see the volt plot, just plot V-O-L-T. Okay. So you can see can you see the plot? No? Yes? Maybe? Yes. Can you see now?
Yes,
Hello?
Prof.
Yeah. That is the volt, V-O-L-T plot. The input. Can you see? Hello?
Yes, Prof.
Can you see? And then the output, okay. Plot DIST. Plot DIST. Okay. Can you see the output? No?
Yes, Prof. You can see.
Can see, eh? Okay. So now we call the what do you call that? IDENT, I-D-E-N-T, the system ID toolbox. Okay. Everybody can see?
Yes, Prof.
Okay. So now we do the business, import data, time domain data. Okay. Time domain data. So there is a Windows outside. So what is our input data? Alkali. The name of the input data. V-O-L-T. Correct. And what is the output data? Shafiq. Shafiq. Shafiq sleeping. D-I-S-T. Okay. Then we put the name HYD. Hydraulics. Starting time is 0.
Prof, we cannot see the screen.
Okay, sorry. Okay. The input data. Okay. The input is VOLT. The output is DIST. The name of, you put any name, you can put name Alkali or Muktaba or Shafi, okay? 0 seconds starting time. What is the sampling time? Sampling time. Tamani. Tamani.
Yes, Prof. Sorry.
What is the sampling time?
Can you come again?
So what is the sampling time? Model A. 45
45 milliseconds.
in second.
45 milliseconds.
Convert to second.
0.045 seconds.
0.045. Thank you. Don't
Okay.
sleep. Huh? Are you sleeping?
No, Prof.
Oh, no. Huh?
No, I'm awake.
Huh?
I'm very much awake, Prof.
Focus, huh? Focus, huh? Okay,
Yes,
so the input is voltage, huh? Yeah, you can put this voltage. The output is distance, okay, or displacement also can. What is the unit for the input? Voltage, huh? V, capital V, and the output is in millimeter, mm. Okay. Then we import the data. Okay, then we close this one. Okay. Okay, come back to here. All right. Okay, can you see the HYD data, the blue color? Hello? Can you see the HYD data?
Yes, Prof.
Yes, sir.
So we want to see the plot, huh? Okay, see the plot. Can you see the plot? See? Okay. The top one is output. The bottom one is input. And right. Now we go to the pre-processing data. Okay, so we divide into two. Select range. Okay, so the data length is 1200. The first half is 1 to 600.
Prof,
Okay.
we can see the screen.
Sorry. There's a lot of windows here. Huh? A lot of windows. Okay, can you see?
Yes,
Can
Prof.
you see? Select range, pre-processing data. So HYDE. E stands for estimation. Insert. Okay, and then it goes to another again. The first goes to this. Okay. So the remaining 600 is 601 space 1200. So we call it as HYDV, V for validated. Okay. See, you can see that we divide the data into two. The first 600 is the green color, okay, for input and output, and the remaining 600 represent in red color, okay. Here, see? Okay, can you see?
Yes, Prof.
Okay, so now we go back to the here. So we have a HYDE, which is the estimation. So we click here, don't lose it, drag to the working data. Okay, close. Then HYDV, click and don't look, click and then drag to the validation data. HYDV. Okay.
Prof, the HYDV data, once we drag HYDE estimation to workspace, we drag HY.
The validation data. Go to the validation data box. We have a working data box and validation data box.
Okay.
HYDE, go to working data box. HYDV, click and drag to validation data box.
Okay, Prof, understood.
Okay. Then we go to the estimate. Okay. So we have a lot of models here. Transfer function model, state space model, process model, polynomial models, nonlinear model, spectral model, correlation model, refine existing model, and quick start. Quick start, when you click quick start, the computer will compute the suitable model for this data using the computer, using the MATLAB solutions. But we want the polynomial models based on ARX331. So we choose the polynomial models. Okay, so there is one box outside, which is this box. Okay, can you see ARX? So it suggests a 441. So we choose a 331 because we want a model structure with 3 poles, 2 zeros, and 1 delay. Okay. So when you click here, the name, it automatically will change to 331. Okay. Then it will use the prediction method, which is least square, then estimate. So you don't have to calculate for the least square. This box, toolbox will calculate for you. Then we estimate. Okay. Estimate the data. There. The data now is outside. So choose here. Okay. So ARX 331. Can you see? 331.
Yes, Prof.
Yes, Prof. Can.
Then you click at the model output. Model output. Okay. So model output, I make it bigger, then I share model output. So Alkali, what is your observation, Alkali? Alkali is sleeping.
Yes, I'm awake, Prof.
What is
Last time I made very wrong observation. Today I have to be very careful.
Right.
Wow.
Just give it. Just give it.
Before I connect.
So
Yes,
we have a black color. We have a
yes.
blue color. Am I right?
Yes.
Okay. If you see here,
Yes.
the blue color here, ARX331 92.11.
Yes.
That is the blue color is the estimated model with 92.11% overshoot. Am I right?
Yes.
So the blue color is here. The blue color, the estimated. Try.
Yes.
Am I right?
Yes.
Nice, huh? Nice, huh? Okay. So this one they cannot follow. And this one also they cannot follow. Okay, lose a little bit lah. But it's okay. It's above 90%. Not bad. Okay. Not bad.
Yes.
Alkali, is it okay? You agree? Okay, so 92.11. So the black one is the real one, okay? The black line is the true model, the real model. The blue line is the estimated model or simulated model. And the best fit is 92.11%. Okay. So we go to back to the toolbox. Okay. So what is the transfer function? So the transfer function, you go to the 331, then double click. Double click. Okay. So when you double click, it will give you a new window. Okay, this window. Can you see this window? ARX331. This is the A polynomial model. Okay. This is the B polynomial model. And the FPE, you browse. See, you can see that the FPE is 0.000. The mean squared error is 0.000 with the predictions of 92.11%. Okay. Right. So that is a 331. If we feel that this data can try a 441, what do you call that? 441 model structure. Okay, why not we give a try? Okay, estimate. Okay, so 441, it looks much better in terms of percentage, right? Okay, see, 94.02 alkali. Okay, so now we have three lines. Black line is the true data, the real data. The blue color is the estimated ARX331 with 92.11% best fit. And the green one is the estimated ARX441, which will give you even better percentage, which is 94.02%. See, increase 2%, okay? But the model structure proposed of 4 poles and 3 zeros. Then how are we going to see the mapping of the poles and zero for 331? So if you want to see one by one, so we activate one and deactivate one. So we deactivate the 441. Then we choose a 0 and poles. Okay, so that is the, here is the poles and zero mapping of Z plane. Can you see? Can you see?
Yes, Prof.
Okay, how to give what do you call that? We said unit circle. How to enter unit circles? Zoom out. Reset to original value. Unconstrained zoom. Horizontal zoom. Vertical zoom. Any idea how to generate what do you call that? The unit circles. Just only zoom. Okay, so we have 3 points here. Zoom out, zoom in. Reset to the original value. Okay, we have an original value here. So I think we can put here. Okay, style. Go to unit circle here. Style, unit circle. Can you see with the unit circle?
Yes, Prof.
Yes, Prof.
And then the grid. You also put the grid. The grid for Z plane is different from the S plane. Okay, because it's a discrete form. Okay, so that is the grid for the Z plane. And how can I get the value? How can I get the value of the poles and zero? Moktaba. Moktaba, sleeping? MashaAllah. Hussein Abrar? Hussein Abrar?
Yes, sir.
How can I get the value of zeros and poles from this poles and zero mapping?
We can use the graph.
Just you click the zeros now. Oops.
Yes, actually there are 2 zeros and 3 false.
But the value, if I want to find the value, what should I do? The value. Okay.
You read from the X and the Y axis.
Read, but if you can click at here, even better. Okay.
Yeah. Okay.
Okay, let's see. I remove the style. I move the grid. I move the unit circles. I move the zoom. Okay. So can I get this value? See? See? I click that. That is the value. I click here. You have to remove the style first. Okay.
Yes.
Okay. Get the value there and get the value there. This is important because you will use it in your assignment, which is due very soon. What is the due date for the assignment?
End in January.
Huh?
End of January.
What date?
Last Wednesday is 27.
Last class,
Last Wednesday in January is 27.
27. Last in the notice I give. What is the due date? Is it next week? 20. The last day will be on the 23rd January. Am I right? Okay, never mind. We will set later because you have to present in front of me. Okay, using what do you call that? Using presentations, half an hour each. Okay, we will set the date of presentation very soon. Okay, so now I will enable the multiple participants can share simultaneously. So I would like to invite Tamani, brother Tamani, to simulate model B. Can you on your video and your speaker? Repeat like what I did just now for model B. Brother Tamani.
Yes, Prof.
Can you share your screen? Simulate model B.
Prof, my MATLAB is giving me problems at the moment.
Your MATLAB will have a problem.
Yes.
Okay. What a good excuse. Right. Can I ask Shafiq? Muhammad Shafiq?
Prof?
Boleh?
Sorry, Prof. I also just uninstall.
Ada lagi excuse. Disappointing. So Hassan Abrar. Hassan Abrar?
Yes, Prof.
Can you share model B with all the class?
I'm doing it now, Prof.
Okay, can you share?
Okay, Prof.
Go to share, enter. Good. Everybody look at Brother Hassan Abrar. Online now.
Sorry, Prof. It's taking to start.
Very fast. i9, Intel 9. It's an online training now, how to use the system ID for data B. Alkali, can you prepare for data C, model C? Oh, Alkali, Abu. Okay.
Yes, Prof.
Model C, standby.
Prof, earlier I messaged you that I
problem.
had some
Problem, Masya. Saravanan Kumar, model C can? Saravanan Kumar? Okay, Hassan Abrar, can you manage?
Yes, Prof. I
Okay.
just opened my MATLAB.
All right. Okay.
Now
Open. Open Model B.
yes, Prof.
Where do you parking your Model B? Desktop. Wait, double prompt. Wait for double prompt.
Hello, Prof. Is it possible to import all the models and keep them on MATLAB?
Sure. Usually I open,
Okay,
then I run. In so many ways you can try.
Okay, thank you.
Sorry, Prof. My computer is really slow. I just
Mashallah. Where do you buy your computer? From Malaysia?
it's 5 years old, so
5 years old. You need to. Can open? Muqtaba? Brother Muqtaba, where are you? Slow, huh? So, okay. If slow, let me show you. Asil, can
yes,
you
Prof.
exit the screen?
Yes, Prof.
Very slow, huh? Your computer very slow. So I will simulate by myself. The reason why I ask you to simulate is because I want you to learn how to use it. So never mind, it's okay. So now we are in Model B, am I right? So you open Model B. Can you see?
Yes, Prof.
Model B. So Model B this is Model B. Okay. So scroll down. Is 1000 data. Okay. Second column input VOLT. Third column output DIST. Okay. Then we press run. Okay, run. Run Model B. Then test the value. Is it insert inside VOLT? And yes, and then DIST. Okay, so the data is there. So we call for ident. Okay, so this one we have to clear this one. Clear first. Okay, so we put in the trash. Okay, trash. Put in the trash. Put in the trash. Can you see the trash?
Yes, Prof.
Okay, trash. Trash. The data you want to throw away is a working data, Windows data. Replace this before you delete the data set.
Prof, may I ask?
Yes.
When you put ident, why is there's a statement say undefined function or variable ident?
That's a good question. Okay.
Is it different version?
Maybe different version. Warning. The ident command is obsolete and may be removed in a future release of MATLAB. So in this MATLAB, I'm using 2018A. So still can acceptable. But if in the version 2020, ident is no more in the function. It's put in another file, but I'm still investigating what is the suitable command for it. Okay, so at the moment, if you're using 2018, yes, you can do it. But you can ignore, simply you can ignore, okay? Don't worry about the red color there. Okay, as long as it goes open.
For 2015, my version, I cannot use ident at all.
Is it?
I cannot proceed to the toolbox.
Because the toolbox is not there. You are not installed completely. So you must choose during the installation complete install. So there's so many toolbox there. Control system toolbox, optimization toolbox, power system toolbox, signal processing toolbox, and system ID toolbox. Okay, so if you put in typical installation, so it will ignore the system ID toolbox. But if you click at the complete installation, so it will include the system ID toolbox. So we read the data here. Volt, DIST. Okay. So you put the name, other name, data, 0.
Prof, we can see the screen.
Yeah. Sorry. Yeah. Cannot see it. Because I'm not sharing. Yeah. Okay. Can you see?
Yes, Prof.
Okay. Time domain data. Okay. Start from 0. But now the sampling has been changed, 45 to 50. So 0.05. Okay. Then we put the voltage, which is for the data level, and the distance. And then input is V, the unit, and the output is mm. Okay. Then import. Okay. Then you see the plot. See the plot. Okay. So that is the plot. Can you see? The top one is the output. The bottom one is the input. Okay. Then after you observe the output, okay. So you go for the pre-processing data for select range. Okay. So we have 1,000 data. So divide by 2, 500 for data estimation. Okay. And then the remaining 501 to 100, 1,000 data V. Okay. So now your data has been divided into 2. Okay. Which is the green data is the first 500, the remaining 500, the red color is for validation, the green for estimations. Okay. Then you go to the box again. Okay. Since this one is the raw data which is not select range data, so you have to drag and drop to data E to working data. The red one, drag and drop to validation data. Okay. And then you use the estimate data for polynomial models, which is shown in the windows here. Okay. So 331, 3, 3, 1. Okay. And then you estimate the data. Okay. Okay. So you can get the model now, ARX331, and see the model output. Okay, so your model output will give the percentage of can you see 94.04%, the blue color. Okay, so the black color is the real value, real data. The blue color is the estimated data. Okay, and what is the transfer functions, the models? Double click at 331. Okay, so when you double click at 331, there is another window, which is shown here with the A polynomials and B polynomials. So the ARX 331 transfer function is y divided by u, which equal to b divided by a. Okay, and to validate the model whether is it accepted or not is 94%. The point is 94% fit, accepted, and then the FPE 0.002, number 2, accepted, and the mean square error MSE 0.00254, accepted, very small error. Okay. Then we go to the mapping. Okay. Go to the mapping. Okay. The others you can see the residuals, the transient response, the progressive response. We go to the mapping here. Okay. So where is the mapping? Reset to the original value. Oh, the mapping is not coming out. Why? Zoom. No. Okay, never mind, it's okay. So we go to the share screen. Okay. So the value is you factorize the A polynomial. Okay. So in this case, you can see that the A is Pohl's polynomial and the B is the zeros polynomial, right? So what should I do if I want to get the value of the Pohl's value? Okay, let's say here, I just if I can copy, no, I can't copy. So you take this A, you insert inside the what do you call that? The MATLAB. Okay, if I jot down the value, okay. So A will be 0.9917 minus 0.1978. Okay. Plus 0.1897. Okay. So that is the A, and the B is you have to factorize 0.1538, which is equal to 1. Then divide by 0.1272. So 0.1272 divide by 0.1538, which is 0.827, and then minus 0.07, 0.7073 divide by 0.1538. So it will give you 0.4598. Okay. So you have to factorize the A and B polynomial in order to get the poles value and the zeros value. Okay. So in this case, I don't. The mapping still is not working. There it goes. Okay, sorry about that. So this is the poles and zero value. Okay. So you can see that we have 3 poles and 2 zeros. Since this is the value of the zeros. Oops. So we have to change at the start. Do not zoom. Do not activate zoom. Okay. So this is the value minus 1.207. 4 zeros. 0 minus 0.4397. The zeros value, the poles value, and the third poles value. Okay. Then you insert the unit circle. Put the grid first, then the unit circles. There you go. You can see that the zeros try to enter the unit circle, but at the moment the status is the minimum, non-minimum phase. Okay. So we change the data. Okay. We change the data. So what I did is, if you want to process a new one, you just delete everything. Okay. No. And then you call back again the MATLAB, right? Go to the main MATLAB. Okay. Then you operate the data C. Okay. So open data C. Okay. So this is data C. Okay. So same, the input is VOLT, the output is DIST. So just check VOLT, is it, the data is there? Oh, you have to run first. Okay, you have to run first. Okay, after you run model C, then VOLT, sorry, VOLT, then DIST. Okay, so the data is there, so you call idem. So ignore the red color. Okay. So now we are processing model C. Okay, so we import the data, time domain data. Okay, VOLT. The output is DIST. Okay, you can put test. Okay, another name. 0. But now the sampling time has been changed to 55 milliseconds, from 45 to 50, from 50 to 55 millisecond. So 0.055. Okay. Then the input is voltage. The output is distance. Then the input is V, and the output is millimeter. Okay. Then you import. Okay. So after you import, you can see that the time plot of the data is similar like previously. Okay. The output and the input. Okay. So we do the pre-processing, okay, by select range. So we have just now the model A 1200, model B 1000, and now the model C is 1500. So we divide into two, 750, okay. Insert. And then another one is 1500, 751. The remaining 750 is V. There you go, that's B. Okay. So the next thing is to drag and drop the estimation data to working data and the validation data to validation data box. Okay, for estimations, we use the polynomial models. Okay, polynomial models, which is here. So we choose as 331. Then you estimate the models. Okay. There you go. That is your 331. And see the model output comparing between the simulations and the experiment. Okay, it's 93.22%. The what do you call that? The estimated ARX 331. Okay. So what is the transfer functions? Just double click at 331 and you get the A and B polynomial for the ARX model, which is B divided by A, with the best fit 93%, FPE 0.00 value, and MSE 0 value. So meaning that, okay, so this is the data for the B polynomial and the A polynomial for model C. And the best fit is 93%, FPE 0, MSE 0, accepted. Okay, the model is accepted. And we see the, what do you call that, the mapping. Okay, we activate the 331 and we see the 0 and poles here. Okay, so we can see the mapping here. Okay, and disable the zoom. Okay, and you can get the value there, minus 0.642, 040, poles minus 0.4426, 0.1441 positive, positive pole 0.3788, and third poles is 0.9995, but still not 1. Okay, and then the unit circles, there you go. Your unit circle shown here with 3 poles inside unit circle, system stable. 2 poles inside unit circles. The status now changed from non-minimum phase to minimum phase with a high sampling frequency at 55 milliseconds. Okay, any questions so far from the students? Is there any questions? Ada soalan?
No, Prof. No questions.
So I will share the YouTube link to you as soon as possible. Okay, and the due date of assignments will be next week. Is it okay? Is it okay next week?
Prof, since you said to end in January, please. And we have 1 week more ahead.
Okay, testing, just testing. Don't worry. Okay, when is the last? When is the last week of the semester?
27th.
27, last.
Yes.
So 27. So when are you going to present? 27? Can you present on 27?
Yes, Prof.
Okay.
Yes.
27. So I will create the timetable for 27 January. Is it okay? So we have another, today is 13, next week is 20, next 2 weeks is 27 January. Is it okay?
Yes, Prof.
Yes, okay.
Fine.
So the due date is 27 January. Then I will set the slot for presentation at 2 o'clock. Okay, 2 o'clock, 2:30, 3, 4 until Maghrib. Okay, I have to evaluate your PowerPoint and your report. Okay, PowerPoint report lah. Your report will be in PowerPoint.
Okay.
Okay, is it okay? Al-Kali, 27 January.
Yes, Prof. Yes, Prof.
Okay, so
Yes.
I ended class here. So I think you can do it now. You know how to use the system ID toolbox. Okay, and I hope you will present it to me on the 27th of January. All of you. We have about how many students here? 1, 2, Tamani, Muhammad, Hussein Abrar, Saravanan Kumar, Muhammad Syafi, Zauji, Mahmud, Muqtaba, Ahmad Hassan. Okay, about 9 students. Okay, 9 9 students.
Yeah.
1 lecturer, 1 observer. Okay, so I see you next week, inshallah. If there is no question, so I stop here.
Prof,
Yeah.
Okay.
then on the but
Tapi tak dengar lah.
what did when submit
Tak dengar. Tak dengar. Chat. Can you chat? Right on chat. Tapi chat. Hello. Yeah, Shafiq, question? Okay, if there is no question, so I end here. Okay, so I will share the link and see you next week. Okay. Muhammad Shafiq said we have to do presentation on 27, but when we have to send the first, oh, no need. Just present the PowerPoint report. Report. I will comment. Okay. I will comment, and you take action for the correction. Okay, for the correction, and submit the revised report via e-learning after presentation. Okay. Okay.
Okay, Prof.
Why I send to Moktabah? Everyone lah. Understand? Okay. Okay. You just present the PowerPoint on the 27. Okay. So there will be a lot of comment lah. I will comment, and then you will take action on the comment. Then you submit into the e-learning. The e-learning that you submit is the final one. The one that you present is just the draft one. Maybe there is mistakes or format. So you take all the correction, then I will evaluate the report based on the last PowerPoint that you upload in the e-learning. And I will evaluate your oral, your soft skill during presentation. That's all for 30%. Understand? Okay? Okay, thank you very much. Okay, and see you next week. Bye-bye.
Assalamu alaikum. Thank you, Prof.
Okay, shukran. Now go there.